I am going to speak on observability. It's such a common topic, and whenever we think of observability, we think of different tools, different frameworks, and it is almost a common topic, irrespective of the type of project or the type of engagement we are in. So the title of the talk came to my mind in a similar situation when I was discussing that about what kind of observability solution to be given to a customer. And Kubernetes is one of the, I think it will be easily among the top 3 or 4 technologies in the last 5-6 years, which is of so much such widespread use, and it has come up and it's going to be there for the next many years, it seems now. So I will start with, I'll start. Okay, so about me, I'm Pratik Das. I joined ThoughtWorks some 5 months back, and I'm in the industry for 20 years. That's quite a long time. And I started with creating distributed applications. I started out as an application developer, but that time also we used to call it distributed application, but which is now somewhat deridedly called as a monolith applications. But still, we had many components which used to interact with each other. We had a front end, a middle tier, and a database, again, interacting with each other. So we had similar problems, but the problems were easier. But now we have Kubernetes. So we'll look into those challenges, what Kubernetes brings to it. So I'll just start with share my screen. I hope everybody can see it. So this is the subject of my talk, how to build observability solutions in Kubernetes. So it is about to understand the audience. How long have you used Kubernetes? Okay, I'll end the poll now. It seems the number is quite evenly spread out between all, but it's good. So I'm going to cover it. It doesn't need any prerequisites. Today's talk. I'll just end the poll here and share the results. I'll stop sharing. Okay, so we'll start with what we do in observability. So observability has there are different things we do in observability. So first is collecting and capturing the different signals. So signals are logs, traces, metrics. So these are the different things we capture. So once we do that, we store those signals in some kind of repository. It could be a database for doing some post-facto analysis. After we store, we do some activities to make sense of those signals. For example, what percentage of customers are not able to log in. It is again from a business perspective, that what do these signals mean to me? And lastly, lastly, we take action based on what those signals are. It could be proactive or reactive. Now, let us see what makes monitoring in Kubernetes so complex. So as I said, traditionally when we have applications deployed on VM, we have only 2 components or hardly maybe another database component. So applications running on a VM, worst case, we have a cluster of VMs and applications are running over it. And then in the Kubernetes world, we have layers of infrastructure. So in the traditional world, we know the application is tied to a particular VM. Any problems happen or we want to see anything, we go to a particular VM to see that what a particular instance of application is doing, what are the logs for the application, and then make sense out of it. So it's a static infrastructure. Applications in Kubernetes have multiple layers. So one is the Kubernetes cluster, which is running units of deployment called pods. Pods are packaged or containing containers, and containers are carrying my applications. So these are different layers. So my actual application is packaged in a container, which is in turn packaged in a pod, and which is finally running in some kind of VM. And again, this is not a static environment. Kubernetes does it's all these are, we call it what is dynamic or ephemeral environment. Kubernetes schedules the pods in one VM or a different VM based on resource availability. So at a particular time, a pod running in a VM, after some time, the same pod may not exist in that particular VM at all. It could be restarted or rescheduled in another VM. So that makes all the observability in Kubernetes all the more challenging. So let us look into the three domains of observability. So in the industry, it's you also called three pillars of observability: the metrics, logs, and traces. But to simplify it, it's just three different types of data. We collect data to make sense out of it. And this data comes in different varieties. So one is the metrics. Metrics are just numbers. We call it telemetry. So these are telemetry information about the applications which are running, the services which enable these applications to run, some kind of middleware, some kind of databases, the virtual machines or the physical machines on which these applications are running. So some kind of numbers about these applications or the physical hardware or the software which is allowing these applications to run. It could be the CPU utilization. It could be the memory utilization. So all these kinds of just numbers, and collect those numbers and try to make sense out of it. So just one category of data. Logs, we already know this is, we have been collecting logs from the very beginning. So if you're an application developer, the first thing you do, anything happens is take out the log of the application and see what's logged in there. And then there are traces. Traces are distributed application, distributed environment, multiple microservices communicating with each other, the request flowing through multiple microservices. So traces are the trace of the request through these different services, how much time the request has spent in each of these microservices. So these are the traces. Combining these two gives a wholesome view of what we call observability. So now we'll go to each of these, understand how these three different types of data are produced by Kubernetes. Then we'll look into how we can extract those data, then store those data, and finally make sense out of it. So we'll start with metrics. So metrics help track the utilization and availability of critical resources such as CPU and memory. So now we are talking of, it's not only the physical machines or the virtual machines, it's the container running over the virtual machines. And containers in Kubernetes are packaged in units called pods. So there is a CPU and a memory utilization associated with it. Based on that, Kubernetes takes many decisions. So introducing the complex nature of Kubernetes here. So Kubernetes produces many metrics. So there are different components. So these are cluster and node level metrics, the container level metrics, pod level metrics, and these are node level metrics. So this is a typo. So what happens is in Kubernetes, when we schedule a pod, we say we schedule a pod because we don't actually run a pod. We make a request to Kubernetes. Whenever we make a deployment to Kubernetes, whether we deploy an application or yes, we deploy an application most of the time. We package the application in a container and then deploy it. So when we actually deploy it doesn't start running immediately. We just make a request. This Kubernetes, please allow my applications to run. And please give me this X amount of memory and X amount of CPU. So this is a request I'm making to Kubernetes. Now, Kubernetes uses this request to allocate some amount of memory and some amount of CPU to my container to allow my applications, which is packaged in the container, to run. So it is up to Kubernetes to take my request and schedule the container within Kubernetes by taking resources out of the cluster from the actual underlying physical hardware. So there can be many errors. So although I've requested for a X amount of CPU and a certain Y amount of memory, that memory or CPU may not be available in the underlying hardware. So there could be two kinds of errors mostly. One is the throttling. If say CPU is not available, so the usual behavior of Kubernetes is it throttles. That means my application will get less CPU, so it will run slowly. And another is memory. I have requested more memory, more than what is available. So in that case, Kubernetes will what it will do? It will evict. We say eviction from the physical node, physical machine, and put it somewhere else or try to restart it. And every time it will, so if my physical memory is not there at all, but still I have requested more memory, sometimes it might get into a loop. So essentially two categories of error. One is throttling, another is eviction, that is errors. So again, this is just a sample of the errors or the challenges we encounter when we deploy in Kubernetes. So to make sense out of it, so what is actually wrong? Why is my application running slowly? Why my application is failing? Why my application is failing to restart every time I'm trying to deploy? I use these metrics. So if the pod is failing, if my application is failing to restart, I look into the pod metrics. If still my application is failing to restart, even if I have redeployed my application, I look into the node metrics. Then I look into the cluster and the node level metric. In the cluster, you have if you see, I have two different categories of nodes. One is the master node, and another is the worker nodes. Worker nodes are the VMs over which my pods run. So these are it can be multiple worker nodes. We call it worker nodes because these are the essential VMs, virtual machines, which are responsible for running my applications. And then there is a master node, also we call it control plane or the controller. This manages the scheduling of the pods in different worker nodes based on the memory and the CPU limits I have requested. Okay, so there are so many metrics, and each of them we need to be aware to track the performance or track the behavior of my deployed applications. And then there are two components called metric server and kube state metrics. I just wanted to highlight, maybe too detailed for this level of talk, but the metrics are again available through APIs. You will see an API server, which is a very key component of Kubernetes and something very useful in Kubernetes. Whatever request we make is an API call to a Kubernetes server. So if I want to deploy a pod or if I want to deploy a application by making some request, I'll make an API call. I want to check how many pods are running in my Kubernetes, I'll make an API call. So I get a set of metrics from the API server also. So once I make a request, this control master node or control plane decides how to deploy in each of the worker nodes. And there is a database also, etcd, which stores the amount of information about number of pods which are running, the state of the pods. So all kinds of information is maintained here. So just to highlight that how many metrics are there and what makes it so complex. And these are not all the metrics, there are so many. So these are just a sample set. Moving to the next one, as I said, metrics we can query the Kubernetes that what kind of metrics are there by running some command line commands. So when we say kubectl is the CLI command for Kubernetes. So essentially it's an API call. I can usually, so if you can see, this is just a REST API. Metrics on node/node name will give you metrics for this node, and pod/pod name will give you metrics for this particular pod. These are simple API calls, but to make our life easier, Kubernetes has provided a kubectl command line through which we access these APIs. And this is a sample of the data we extract by running these commands. So as you can see, that it's a CPU usage. You can see the usage in terms of CPU and memory. From metrics, coming to logs. Logs in Kubernetes are a bit different. Traditional world, application writes to a log. Application is running on the VM throughout its lifetime. If it dies, the log is still remaining. But in the Kubernetes world, my application is running in a container. As I said, this container can be allowed to run by Kubernetes as long as the memory and the CPU is available. If the memory and CPU is not available, the container or the application will be evicted out of the node. So that time the log for that container will also be evicted. So as long as the container is running, the container will be writing the logs to that particular node. So these particular log files I need to aggregate. So these log files are not constant because the application is keeping on running and the log files are also being written down. So if the application is not dying at all, it's not evicted or does not, even in restart, this log file still remains. So Kubernetes automatically rotates the file. It logs the file to a particular size and then it rotates the file. So you will be losing the logs. And as I said, if the container is evicted, you will lose the log anyway. So we need to handle this a bit differently. So the usual way of doing in Kubernetes is aggregate the log. So capture the log, convert it into some format, and then ship it to a central location where we get it even after the container is dying down. So we spoke about container logs. Similarly, we have node level logs. So that is the performance or the information that how the node is behaving. So that is the node level log. Audit log, who is performing what kind of activity in Kubernetes, useful for security or the regulatory reasons. That who has performed any changes, who has created a cluster, who has created additional nodes on the cluster, any kind of patches have applied. So this is the audit logs. Event logs, it's full of events. Or not pod getting initialized or pod getting restarted. These are examples of some events. It's full of events. So events also, there are logs, we can see different type of events and we can see how the particular state of the cluster is depending on the series of events. Ingress logs, ingress is a very important part of Kubernetes. The Kubernetes cluster has everything, the microservices running inside it. But how do you access these services from outside the cluster? So that is done by a component called ingress. So ingress is again, Kubernetes does not give an ingress on its own. It's a specification and we apply different components like external third-party components like Nginx as an ingress, which allows communication from outside the cluster to components inside the cluster. So you will be interested in ingress logs also. So what happens if I'm not able to access a microservice which is running inside the Kubernetes? And finally, the API server logs. So one of the most important components in Kubernetes, because if the API server is down, you cannot access Kubernetes, even though the cluster will be running and perfectly healthy. And just one more thing, std out and std error. By default, the default behavior of Kubernetes is applications can write to standard out and standard error. These logs are written to a log driver. These logs are finally output to a log file, which is stored in the node or in my VM machine, the physical machine or the virtual machine on which my pod is running. So I can just log into my machine, go to a particular folder and see the log file. But as I said, this log file is ephemeral. If the container dies down, it is evicted. This log file will also be evicted. Okay, as I go along, if you have any questions, keep putting those. So I'll be taking those towards the end or in between also. Okay, from the logs, so now we are moving to tracing. This is also called the third pillar of observability. So we call it distributed tracing. So this is a bit different. We were not doing it that much earlier in the earlier world when we had static applications and virtual machines. But now, since we have so many microservices communicating with each other, this particular pillar becomes very important, maybe one of the most important part of observability. So let us understand what distributed tracing is, and then see how we capture this information. So distributed application is composed of multiple microservices, multiple units of application. This A, B, C, D, E, all of these are different microservices communicating with each other. So A makes a call. So for fulfilling a request, a user or some other service makes a call to A, microservice A. For fulfilling the request, A makes a call to B, B makes a call to C. So it's a series of requests going all the way to E. And finally, this call returns back and finally comes back to A. So the total time taken by the request which is coming to A is the sum of the time taken by each of these microservices. So that is what we call trace of this microservice through the services B, C, D, and E. So how do we capture it? So we capture it through two data entities. We call it, one is the trace, another is a span. So this is a single span of a request. So it spans across these 5 services, A, B, C, D, and E. And this span is composed of a trace on B, a trace of C, D, and trace of E. So if we can see this, the horizontal dimension is the time. It is completely occupied by A, and it is composed of B, C, D, and E. So this is how we capture it. So essentially a span composed of multiple traces. So span is a unit of work. Example is an HTTP request, and a trace is a collection of span connected in a parent-child relationship. And traces specify how requests are propagated through services. Now collecting and storing traces. So as you can see, this is then application plays a big part in how we capture these traces. So previously logs and metrics, these were all of these were outside my application. My application is running and I'm essentially observing the infrastructure, that how it is behaving, and then capturing those metrics and logs. But trace is something which I need to do inside my application. So I need to do some kind of instrumentation in my application. Just like for logging, I do something in my application by producing the log. So this is usually the flow taken. We have applications which takes an instrumentation SDK. So the instrumentation SDK is responsible for creating those traces. And then it creates these traces and sends it to a particular agent. So agent is again another piece of application which is collecting those information, buffers them, and sends to another component called collector. And this collector is sending it to a particular storage. Now we have a different tooling landscape. So many tools in this for observability. So you have commercial tools, you have open source tools. So each of these tools have something in common. Everybody has some kind of storage, because without this storage, you cannot make sense out of the logs. And everybody has a collector. So the role of the collector is get the data, convert it into a format which that particular tool will be able to understand, make sense out of. So these two are very important parts, collector and the storage. And there is something common I wanted to introduce, something called open telemetry. Open telemetry has come up as some kind of a standardization effort in this industry. Open telemetry gives you SDKs and libraries in different programming languages. Here I've given you 2 examples. One is from the Java world, another is from the Node.js world. And these are again 2 different ways of capturing the traces. Java is using the agent jar file at startup, and Node.js is doing something in the application. So there are different levels of maturity when OpenTelemetry provides support for providing the instrumentation SDK for different languages. Earlier, there was no support for Golang, but now I see the support for Golang has also been added. So gradually this OpenTelemetry is maturing, and it's a consortium of different vendors who are working towards standardization. And what they do is they create some kind of instrumentation library which is common, which all other vendors will be supporting. They provide a collector component and they provide an agent. And then each of them take these collectors and convert it into their own format for their respective storage components. So this is an example of a sample trace in a Jaeger UI. Jaeger is another component, another tool in the CNCF used for used for distributed tracing. So this is how the tracing has been captured. So you can see the order service is broken down into multiple traces and multiple spans, and each span consisting of multiple traces. So you can see the timeline as a horizontal axis, and that each of the service in the vertical axis. Fine. So we came across these three types of data. One was the metrics, which is just numbers or figures like CPU percentage, CPU utilization, memory utilization. Second was the logs, and the third is the traces. Now we are getting into alerts. So one of the most important thing, because we monitor these three data points, one alert, logs, and traces. Now we need to alert the user, alert the end user, and alert the systems that what went wrong or something I need to be actioned. So how does this alert rules look like? So alert rules are defined mostly on metrics. So it can be that the CPU percentage or CPU utilization is exceeding a certain amount. Then this rule 1 gets fired. So once the rule is fired, a component called alert manager, where we define the different kind of routes. These routes will be sending notifications to different systems. It could be emails, it could be Slack, or it could be even we can integrate it with other systems to take some mitigating actions. So this is a basic structure of the alert rule, again implemented in different ways by different tools, whether open source or commercial. This is again another sample of how an alert rule will look like. So this is a definition of an alert created in Prometheus. So Prometheus failed to scrape X percentage of kubelets. So this is how we have defined it with an expression, that kubelet job and divided by some count kubelet job greater than 0.03. So when I'm saying kubelet, I'll just explain what a kubelet is. Kubelet is the process which is running in my nodes, which is responsible for scheduling different containers or the pods on my nodes. So when I say node has two processes which are always running. One is the kubelet process, one is the node process. So each of them produces their own metrics, their own logs. And once the alert is fired, we see this kind of alerts in the as a notification in Prometheus. So again, different tools have different ways of firing the alert. Okay, after covering this, finally, we are getting into the heart of this talk. That is, what tooling do we need for Kubernetes observability? So there are so many ways. We saw there are different types of data Kubernetes produces. That data, each of the data can be accessed through APIs. It can be it can be consumed in different ways. The nature of the components are ephemeral. It's dynamic. Most of the applications packaged in pods are short-lived components, depending on the capacity of the nature of the utilization in the node, and could be evicted or scheduled in another node. So these are short-lived components. But we have all kinds of data. Kubernetes is emitting lot of data. So from all its components, whether it is the API server, whether it is a node, whether it is a pod, whether it is a scheduler, kubelet, everybody in all the components is emitting data about its health, or we can make some kind of sense out of the data. So we can easily build something of our own. If there are APIs, I can scrape the API, I can pull the API and make sense out of it. And let us look into it in the next slide. Then there are SaaS solutions, software as a service given by vendors. And as it says, in SaaS, the conveniences, we don't have to manage the infrastructure. And the last is the cloud native. Cloud native ones are available in the cloud solutions, because most of the Kubernetes distributions are, most of the cloud providers are giving Kubernetes as a managed service, whether it is AWS giving EKS in the Google world, we have GKE. In the Azure world, we have the Azure Container Service. So all the AKS, it supports, these are given as managed services. And along with that comes many observability tools, which are default with to the cloud providers. But often these are not enough. So if you see CloudWatch in AWS, you get everything with respect to AWS only, but it may not be enough. So let's see in the next slides how it can be. So this is the first one, build your own with open source tools. So when we build our own observability solutions with open source tools, we look into these 4 aspects. One is data collection. So first point is, how do I collect the data? So one is manual way. Manual way by running kubectl logs. Okay, I was just thinking of executing some of these commands. One, I'll just come to the end of this presentation and then execute some of the commands and see some of those tools. Okay, so first is the data collection. So it can be manual by running kubectl logs command. We get a series of logs. You specify the pod name or the node name, and you can get the logs in your command line, and then do some kind of tooling shell scripts to aggregate the logs using some log tailing. Then open telemetry is, I introduced it as a standard which is available. Specification based on open telemetry. Also, you can build some tooling, and you can use many open source tools which are based on open telemetry. Then Fluentd is another option which does log aggregation, because there are so many components creating the logs, and we need to aggregate the logs and put it into some kind of storage. Prometheus is another way of collecting the logs, which works on the basis of scraping the metrics. We saw that metrics were created from using an API, and we can scrape those API or pull the API at particular intervals, pull those metrics and store it in a database. And Jaeger, I showed in the previous slide that how it captures traces produced by different microservices connected with each other. Storage is one of the most important aspects of when we think of open source tools. Storage is it's a mandatory. So because since it's a ephemeral system, we need to keep collecting data and store it in a repository. So this is usually in the nature of time series databases. Most common ones are Prometheus, InfluxDB, and Cassandra. So the data is stored and then it is used further for analysis, or it can be queried by other visualization tools. For visualization, common tools are the Kubernetes dashboard, which comes default with Kubernetes, or some distributions don't give it by default, where we need to install it. And then there is Grafana. Grafana is a very popular, or one of the most used widespread in this domain for visualization, which connects to Prometheus or other time series databases and provides some useful visualizations. And Prometheus, I missed. Prometheus also allows you to create useful alerts with which you can send notifications to different systems. And also you can configure applications which you can work on those notifications. And then there is a query and analysis options also. There is PromQL on Prometheus and Kibana query language on Kibana, with which we can run powerful queries based on the data which is stored in our time series databases. But essentially, it's a collection of tools. Either you build your own. Mostly we don't. We look into the open source world. There are plenty. So we look for a data collection. Either we look for Prometheus, or in the ELK side, we look into the Elastic Stack. And similarly, on the visualization, we identify one and then we put those together. So I've just taken the two used most commonly in this area. One is the Prometheus-Grafana combination, another is the EFK or the ELK stack. Prometheus, as I explained, it works on the basis of scraping metrics from the metrics API and storing them in a time series database. And once it is stored, we use the Grafana tool to visualize the data which is stored there. Similarly, on the EFK side, we use, because since the logs are always temporary based on the lifetime of the pod, we need some kind of collector which will read those logs and send it or ship it to a central location. So one type of collector or aggregator is named as Fluentd. There are other variations also. Elastic has its own agent now called Elastic Agent. There is a lighter version of Fluentd called FluentBit. But the idea is same. So these are essentially deployed in the node as a daemon set. Daemon set is just like I have multiple pods running in a node. Daemon set is only one instance of the container running within the node. So this collects all the logs inside the node and ships it to a central location, that is Elasticsearch. Elasticsearch is again another example. It's just an example. I can have other central log repositories where the logs can be shipped. And then finally, I have a visualization tool like Kibana, which connects to Elasticsearch and where you can visualize the data and run our analytical queries. Full stack SaaS solutions. So these are, as I explained, here we don't have to maintain our own infrastructure. If you recall, in the open source world, we need to select our tools, different tools for data collection, storage, visualization. So it's not only tool selection, it is also the infrastructure we need to maintain, that how much storage we need to allocate to the database. If the volume of my logs, if I'm producing a lot of logs, so whether it is going to slow down my transactions. So do I need to do some kind of buffering? Sampling rate. Sampling rate is also a very important criteria or something we define to not to take all the data, instead of take only a sample of the data which is useful to me. So that helps reduce the noise created out of so much data. Creating smart alerts, because we might create alerts on so many metrics. So in which metrics I should look, and a limited number of alerts which will be useful to me. So SaaS solutions come up with a lot of things inbuilt. First is they take care of the infrastructure, so that you don't have to take care of the infrastructure. The storage is taken care of. The way you write to the storage by buffering or buffering into an intermediate layer, those are taken care of. And powerful analytic capabilities, AI, machine learning based tools are also available. So they come with a lot of capabilities. So when we select, when we go for a full stack SaaS solution, we look for these specific things. What kind of capabilities we should look for? One is data collection. So automatically discover resources. So since my resources are, I will keep on adding my new applications into my Kubernetes cluster, create services out of it. I should be able to discover the resources automatically. I should not be needing to configure my application or configure my log collection agent every time I create a new resource. So it should be able to discover automatically. It should be able to detect the state changes from all the layers and components of Kubernetes, because all the time the state of the pods changes. It could be starting, it could be running, it could be on the verge of being evicted. So it should be, I should be able to detect, and based on that detection, I should be able to create alert. Using open source collectors to collect logs, metrics, event, and state changes. As I explained before, using an open source collector like OpenTelemetry is very important, because that allows you to gives you some kind of flexibility of switching tools at a future date. Because as long as they are compatible with OpenTelemetry, the amount of changes in your infrastructure may be minimal compared to if they are not following any standards. Usage-based pricing, separation of compute and storage cost. So there are different models on which these SaaS solutions are based. One of the old model, I'll say, is based on the number of cores which are being used. So based on the number of cores in the nodes, the pricing is done. But usually, since you can run any number of pods in your Kubernetes, sometimes that pricing may not work out well. So essentially, it is separation of compute and storage cost or other new models of pricing based on the elastic nature of Kubernetes. Visualization. So visualize availability, performance, and dependencies. I should be able to visualize in my tool. So it's not only the metrics randomly. Availability, performance, and dependencies between the applications should be, so it's actually making meaning out of those metrics in terms of availability, performance, and the dependencies between those business applications. Creating alerts based on my metrics and state changes. We saw an example of from Prometheus, how we were creating alerts. Giving information on the context. So you have a container which is dying down. So what is the context of that? Whether the load, whether the number of requests, customer request has suddenly peaked up. What is the context of that happening? And predictive problem detection. So based on my historical data, can I predict that my node is going to go down? And query analysis, one of the important features I've seen is the time travel. That a complete change log of all events through which I can reconstruct the state of my cluster.
Sorry, like just there are 5 more.
Yeah, I'm almost towards the end of it. So this is the last slide in my presentation. So observability, we saw it's only about tooling, but we also need to go beyond the tooling. So first is we need to set goals, that we set up goals for observability. That what will be the first is it should be understood by all stakeholders. So everybody needs to understand what this particular metric means to me. A single first pane of observability. Example is, first should devs look at when things go wrong. What is the first place where I should be looking at? I should have alerts and metrics and then dig down to logs. So essentially a process of finding out problems. Continuous improvement. So establish measures like MTTR, mean time for resolution, or mean time for detecting an error. Setting alerts on SLIs rather than an individual metrics. Some kind of feedback loop that if my solution is working out. And always building the solutions for scaling, that the system or the infrastructure should not break if the load on my system increases. Fine, with that, I'm coming towards the end of it. So you can take some questions.
I think there are some questions in the Q&A section.
Yeah, I'll just going through that. I'll start from the top. Sapan asks, does Kubernetes emit these matrices by default always or have to be enabled? Again, it's a mix of both. Some of the matrices are by default, some of the metrics you need to enable. So API metrics, for example, are not available by default. You need to enable those. And similarly, at the application level also, sometimes these metrics become useful. So there are some programming languages also where you need to enable those metrics. So you can analyze the application metrics together with the infrastructure metrics. But a good percentage of Kubernetes metrics from the node and the pod are available by default. So answer is it's a mix of both. Okay. Venkat, the question is, can you please throw some light on high-level architecture of managing population scale video chat applications using APIs in a few sentences? Let me understand. Can you please throw some light on high-level architecture of managing? I think this question is not on this topic. Maybe I can take it offline if there is interest, how it is related to Kubernetes. So I'll move to the next one. Nithya is asking, does tracing impact the performance of application? Yes, to some extent it can. And that is where I was talking about making designing your observability for addressing scaling, observability at scale. So this is the solution I was talking about. One is there are some configurations you need to take. So if you put a default solution, it may not work out once you are running your applications on a scale. So some of the problems we might encounter is the sampling rate. So you keep collecting everything and then trace everything. So sampling rate, if you configure some sampling rate that I only take 40% of the traces and then I log those. So one is sampling and another is, you saw those layer between the collector and the storage. So between the collector, instead of the collector directly writing to the storage, so it's a direct synchronous calls. You can put some kind of asynchronous layer. So take those data in some kind of Kafka layer and then let a Kafka connector send your data to the storage. So these are some performance improvements you can do for handling those. But that doesn't mean you don't do OpenTelemetry at all, because these are some of the useful tools which will help you to trace that what is wrong with your application or why your application is running or slow, or do some troubleshooting. Last question is from Prabhakar. Any idea of Datadog? Is it useful with Kubernetes for monitoring, alerts, analysis? How does it compare with other tools? So again, Datadog is a SaaS solution. It has, just like I explained about the tools, Datadog gives you an agent which you need to deploy into the Kubernetes. So the job of the agent is, one is to collect the different log data and put it in storage in Datadog. So the storage is owned by Datadog. The agent is given by Datadog. So at the same time, it collects metrics and sends it to a storage, and then it gives you some analytical capabilities by using some machine learning libraries, which will help you to do some kind of prediction also. So Datadog happens to be one of the SaaS solutions in the market, as opposed to there are other tools also like Dynatrace, App Dynamics, New Relic, Splunk, so many. So Datadog is just one of them. Any other? Prabhakar. If I want to switch from Prometheus-Grafana stack to Hotel, how mature is it and what are the constraints? So Hotel is not a standalone solution, I will say. So Hotel, you need to integrate other solutions also. So Hotel will give you a limited functionality. It is just a collector. But what you do with the data collected, so you will still need need Prometheus and Grafana. So Hotel is just a collector. It's not a solution on its own. So these are complementary. These are not solutions. This Hotel is not a standalone solution, I'll say. Then what is the, no, what did I miss? Our question is related to distributed systems in the cloud. I don't get this question. If anybody can explain, it will be better. So in the meantime, I'll go to the next one. Kubernetes with Elasticsearch on Bitbucket pipeline. Can you share any useful docs if possible? Kubernetes with Elasticsearch on Bitbucket pipeline. No, at this moment I can't. I am not sure. Elasticsearch and Bitbucket, I understand it very well. So I'll just need to check this. Elastic Shards has the potential to bring down the storage pool that it is residing in if a shard consumes the entire volume. What is the best practice for storing telemetry data? There are several best practices. This you are getting into how you can scale your observability solution. One is configured, one is definitely increasing the storage. Another is sampling rate, increase the sampling rate so that you don't consume everything. Make some optimizations on the logs you are producing, logs and metrics you are producing. So you may not be interested in all the logs or all the matrices, filter it at that level only. So just disable the logs or metrics producers which you are not interested in. And then finally, you can add a Kafka layer. So instead of writing directly to the database, take it into Kafka, then do some filtering on the data you are interested in, and then stream only those data which you are interested.
Pratik, there is one question from Gurgaon office. Rishabh, can you go ahead?
Yeah, hi Pratik. When a critical on-call happens, how Jagger UI helps and what are all the steps infra team takes usually?
So that is what I said. Observability is something which goes beyond tooling. So ideally, you should have a process in place that what is the first thing I should check when incident happens. Whether I should go to my Grafana dashboard or my Kibana dashboard where I have defined a certain metrics. What is the first metrics or thing I should check that what has happened? So I see a certain metrics going out of a particular range, or if it is log, it could be log. I have configured a log anomaly detection that I can see anomalous log happening. So again, you establish a process, and it is based on a set of historical incidents we have been through the past. So you establish a process that what is the first place I should check, what I should check, whether it is a metric, whether it's a piece of log, whether it's an anomaly which has happened in the log, whether it's a discrepancy which I observe with the metric, and then take those actions. So the follow-up actions could be check a particular log in a particular node or a particular pod, whether I'm experiencing some kind of throttling, whether I'm experiencing some kind of eviction, or suddenly the load has increased or something has happened. So these are some of the things you should do. So instead of directly jumping into the Jaeger UI. So the last thing which comes is the tracing. Then you pinpoint the applications or the microservices which have been impacted, and then you go through the tracing. What is the request path which it has taken through the microservices to find out the problems are in which particular microservices. So starting from the top and pinpointing it to the microservice which is responsible for causing it, or it is the infrastructure, whether it is a node or any other component in Kubernetes cluster.
Insights tool which is available, which you guys are using, like when we start from the Grafana dashboard and then we go towards tracing. So any particular tool which is giving you insights about all of these things?
These are a collection of tools. So that's why if you compare a open source tooling with a SaaS solution, so SaaS solutions essentially you are using one tool which gives you most of the answers. At least you will find different avenues without going into different tools. But if you are in the open source world, you have many combinations. Sometimes I've seen people using both Grafana and Kibana, a mix of both Grafana and Kibana, and also sometimes going to the Prometheus dashboards to look into their alerts. So that is where the establishing a process based on historical actions becomes important. So I'll not name a specific tool, but essentially the focus is on how mature your process is based on your historical actions which you have taken for resolving incidents.
Thank you.
Thanks, Prateek. There is one more question. So, what's the difference between data engineer and a data scientist? And what is the roadmap we should take? This is question from Aditi, Gurgaon.
Is this data for me? Is this a question for me or Anshu? This is an observability. Anyway, let me. So I'll say a data engineer is a person who engineers the data. So who works with these different tools like Azure Data Factory or any other data tools. AWS Glue, take the data, make sense out of the data by running tools like AWS Glue, understand the metadata out of the data. So it is running those engineering, running those queries, extracting the data from the data sources, understand those variety of the data, what kind of data is there, and writing some scripts to do the processing. So engineering is doing the sort of coding, I'll say, engineering practices. Data scientists brings a high level view. He brings an understanding that, okay, so this is the approach I should be taking. I should be looking at this category of data to make sense out of it, making a business sense out of it. This is the sample of data I should be analyzing to do some predictions. So for making do some predictions, this is the sample, or these are the varieties of data I should be capturing. What should my test data look like, and what kind of output which I will get? So this is the job of a data scientist. So I'll say data engineer is more hands-on with and more closer to the tools and the writing queries and all. And data scientist is more at a conceptual level and bringing in strategy and advisory. This is the difference.